Good evening, everyone. Welcome back to another domain analytics session. So we'll be continuing on with our analysis of financial security. And today we'll be taking a look at a very interesting topic that deals with money laundering. Right. So now money laundering is a way of whitewashing your illegitimately earned money and presenting it as legitimate money. So this process involves channeling the money through various financial institutes, and these financial institutes would then, over time, the origin of the original source of the money would be hidden, and you would end up with clean money that can be used for anything without any objections. Okay, so preventing money laundering is quite a big deal because you are having nearly $2 trillion of money being laundered every year, and that is nearly 5% of the world's GDP. So you're already losing out on a huge amount of potential money that could be used for other purposes. So let's take a look at it. So in order to deal with this, we'll be shifting our focus on supervised machine learning. So in supervised machine learning, our output is known. That means we already know what output we are going to be working with. Okay, so the output is known. So we follow a different procedure than what we do in unsupervised machine learning. You have your historical data. You take a random sample out of it. You split this data into train and validation. You train your ML model. You get some equation. This equation is going to give us the solution for our problem. Then you validate the equation. Then you validate the equation, and after validating the equation, you end up with some accuracy and validation error. Until the time where we have a very good validation error or accuracy, we keep repeating this loop. Okay, once it is done, we get a final ML equation. Using this final ML equation, we take new data, or we take a test data. Using this, we make a prediction. Prediction using this final ML equation. All right. And then we get a predicted values. So this is the basic stage of these are the basic steps for any supervised machine learning algorithm. Okay. So today we are going to be taking a look at an algorithm called K nearest neighbors. So we are trying to classify data points based on how many data points are nearest to it. Okay. So this is the easiest machine learning algorithm that you can implement within supervised learning, and it can be used for both regression and classification. So the difference between regression and classification is here the Y is continuous, and here Y is discrete. Okay. So we can use it for either classification as well as we can also use it for regression. So let's move forward. So today we'll be taking a look at nearest neighbor classifier will be taking a look at 1 nearest neighbor, 2 nearest neighbor, 3 nearest neighbor, 8 nearest neighbor. We'll also be taking a look at how we can classify a k nearest neighbor, how we can control the complexity in KNN, what is Euclidean distance, and finally, we'll be taking a look at some hands-on experience for this. So we have this image. Now, within this image, we have this object 4. Now, we don't know if this is 4, but we want to classify it. We want to assign it some class. So how do we go around to assigning that class? We try to find the nearest values to it using some distance metrics. This distance metric will calculate the distance for this point 4 to all other points within the data set. And whichever neighbors are closest to it, it will be assigned to that value. So here, if we are trying to assign this 4, we will probably assign it to the class 4 itself. Okay. So then let's take a look at it. So we have one nearest neighbor classifier. That means we are only taking one nearest neighbor. So we have this new data point here. This is a new data point. We are trying to calculate the distance between each and every point. Okay. We are trying to calculate the distance from this value to each and every point. Okay. So using this distance, we can see which object is closer to it. So here we can classify it. All right. Similarly, if we had a data point that was somewhere here, we'll try to find the distance between this data point to all other data points, and we'll classify based on whichever data point is closest to it. Okay. So this is what we call as one nearest neighbor classifier. Okay. And then we can do two nearest neighbor classifiers. So we have to specify how many nearest neighbors we want. So here we can have two nearest classifiers. So here we have taken the Euclidean distance to every data point, and we have found the data point where our new data point is closest to. So we have found this data point and we have found this data point. If we had this data point over here, we'd probably find something that looks like this. So it can change based on where you place it. If you place it over here, it might look something like this. Okay. So we are assigning it some nearest neighbor. And based on that neighbor, we are classifying it. So this is when you take two nearest neighbor. Similarly, you can take three nearest neighbors. You can try to classify it based on its three nearest data points. Again, the concept is quite similar. You're taking a data point, a new data point, and you're trying to find the distance from this data point to its nearest three data points. But you are calculating the Euclidean distance for all three data points. You are calculating how much distance is there between this point and this point. All the points you are taking. It doesn't matter how far or how close it is. Okay. So this is what we call as three nearest neighbor classifier. Now you can also take 4, 5, 6, 7, 100, 1000. It really doesn't matter how many nearest neighbor you take, as long as you're able to properly classify them. So then we take a look at the next one. Here we are classifying it based on 8 nearest neighbors. So we have the data point over here, and we are classifying its 8 nearest neighbors. Okay, so these 8 nearest neighbors are the 8 closest point for this specific data point. Okay, so here we have taken 8. Now let's see. So now we are trying to control the complexity of the data. So here what we are doing is we are getting a training accuracy. Now this training accuracy will keep on increasing as you train more. Of course, as you keep, training more and more, your accuracy will keep on increasing. And as your accuracy keeps on increasing, you are thinking that, hey, I'm building such a good model that I am getting 100% accuracy in training. That is not always a good thing. Okay. So what we are trying to do here is we are also trying to take the validation set accuracy, whatever the validation accuracy is. And we are trying to find the peak of this accuracy. Where is validation accuracy peaking? Is it peaking at 80%? Is it peaking at 90%? Is it also peaking at 100%? So this information we are trying to find. Now, if your validation accuracy is, for example, let's say peaking at 60%, that is not good. Okay. And if it is peaking at 100%, that is also not good. That means you have done some error while you were doing the model building. Okay. So what we are trying to find here is what is our accuracy percentage. So we are trying to find a good level of validation accuracy. Now, in order to find a good level of validation accuracy, we use hyperparameter tuning. We are tuning the hyperparameters we have, but the important point to denote here is that KNN is non-parametric. That means it is not taking any parameters aside from how many neighbors we are going to specify. Okay. And we are already seeing similar example in k-means where we are iterating through a different group of nearest neighbors. Okay. So we are already iterating through a different group of nearest neighbors. So what we are trying to do here is we'll specify the total number of neighbors, and will not just specify one nearest neighbor or two nearest neighbor, we'll specify a range. Okay. And within this range, we'll try to find our correct number of k. So we are already testing for different number of neighbors, and we don't have any other parameters to take. So we cannot apply hyperparameter tuning on this. So in this, we have to go back to our pre-processing and as well as our feature engineering. Maybe we need to work better on our PCA. Maybe you need to do better pre-processing. Maybe you have let outliers sneak into the data. So all those things we have to keep in consideration whenever we are getting accuracy that is not what we need. So let's say, for example, at this point, we'll call this point A, our training accuracy is 60%. If your training accuracy is 60%, you directly go to these steps. Okay. Now, for example, let's say this is actually 90%. Then you go to your validation dataset. Validation dataset at its peak is depicting 60% accuracy. You again go back to this step. But if we are able to increase that 60% to, let's say, 80%, suddenly we can perform a lot better. Suddenly we can say that our model is performing as expected. It is doing as expected. So this is where we will stop training. Now, training accuracy is continuously going up. So you might get a scenario where training accuracy is 100%, but you notice here that the validation accuracy has started falling off. And the validation accuracy is 40%. Then it is pointless. Then it is simply pointless for us to try and use this value of K. Okay, we want to take the optimal value of K, and this is how we find the optimal value of K. So now we have this data set. Now what this data set is doing is, it is trying to classify food items into fruit, protein, and vegetable. Okay, it is trying to classify these items into fruit, protein, and vegetable. So you have apple with 10 sweetness, 9 crunchiness, and this is classified as a fruit. You have bacon with 1 sweetness and 4 crunchiness, it is classified as a protein. You have banana, which is classified as a fruit. So wherever the sweetness is higher, it is classified as a fruit. Wherever the crunchiness is higher, it is classified as a vegetable. And then you have cheese. Cheese is also classified as protein. Both sweetness and crunchiness are low. So what we can do here is, we can group these items together. So we can create 3 separate groups. So these are our proteins. These are our vegetables. This is our fruits. Now let's say we introduce a new fruit in this. We take strawberry. Now strawberry, for example, let's say the sweetness is 9, crunchiness is 5. So strawberry would get classified in fruit. Okay, but similarly, we can also find the Euclidean distance. So in this scenario, what we try to do is, we try to find the Euclidean distance of strawberry from each data point. So for example, let's say we have apple with 10 sweetness, 9 crunchiness. So we find the distance. The distance would be taken as 9 minus 10 square plus 5 minus 9 square. This becomes 1 square plus 4 square, that is square root of 17. Similarly, you can find the distance to, for example, let's say we have carrots, that is 7 and 10. So that would be 9 minus 7 square plus 5 minus 10 square. So this becomes 4 plus 5 square root of 29. So based off of this, we can say that strawberry is nearer to apple than it is to carrot. You can also calculate the distance from green bean, cucumber, celery, nuts, bacon like this. And the model will calculate the distance from each and every data point. Okay, it will calculate the distance from each and every data point. So that is how you do it. So now we have tomato. Tomato is given the rating of 6 and 4. So which item, food group does it belong to? Does it belong to vegetables? Does it belong to fruits? Or does it belong to protein? What you do is you take the sweetness and crunchiness value. So this would be a x1 and x2. Sorry, y1. This would be a y1. Okay. So what you do here is you take the Euclidean distance. Right now we are taking the Euclidean distance. You can take x1 minus x of I square plus y1 minus y of I square. This I square is the crunchiness and sweetness value of all these objects, whether it is fruits or vegetables or proteins. So we try to calculate the Euclidean distance of it from each and every data point. And then what we have to do is we have to specify how many neighbors to take a look at. So let's say we are starting off with one neighbor. Now, after your calculations, you find out that the distance of tomato from orange was 5.0 and from green bean was also 5.0. So where do you classify this with 1? Probably not the best idea to classify using 1. It would not belong to any of it. What about 2? Can we classify using 2 neighbors? No, we cannot. Because even with 2 neighbors, it is not making any sense. Let's say, for example, the grape distance is 5.83. This distance is 6.0. Okay, let's take 3. So in 3, we notice that we have 2 fruits and 1 vegetable. So we can probably classify this as a fruit. So in order to avoid a situation where there is a tie between 2 categories, fruits or vegetable, fruits or protein, vegetables or proteins, we use odd number of neighbors. We use odd number of neighbors. Okay. So we try to find out how many odd number of neighbors we have, and based off of that, we can decide the total. We can decide where this item should be classified as. Okay, so it can be classified as a fruit, vegetable, or protein using this formula. Okay. So this is our Euclidean distance formula. So however many variables we have, we can use it to calculate the Euclidean distance. We can directly use it to calculate the Euclidean distance. That's it. We don't have to look at anything else. We really don't have to look at anything else. Okay. So Euclidean distance is the standard formula, but you can also use something we call as the Manhattan formula. Manhattan formula is basically x of 1 minus, what do you call it? X of I absolute value plus y of 1 minus y of I absolute value, like this. Okay. So you can use Manhattan distance as well. Okay. So this is how you classify objects in K nearest neighbors. Now, what do we do for evaluation? Now, let's assume Y is categorical. When Y is categorical, we are trying to build a confusion matrix. Okay. This confusion matrix will have true positive, false negative, and true negative. This will give us how accurate our classification model is. So we can calculate the accuracy, we can calculate the error, we can calculate the precision, the recall, the sensitivity, and the F1 score. So we can calculate any of these metrics. Okay. So accuracy would be true positive plus true negative divided by true positive plus true negative plus false positive plus false negative. And error would be classified as false negative plus false positive divided by true positive plus true negative plus false positive plus false negative. Okay. So this is how you can calculate the accuracy and error using a confusion matrix. In case Y is numeric, mostly we are saying continuous. When Y is continuous, what you use is error functions. You can use the mean error, the mean absolute deviation, the mean squared error, root mean squared error, mean absolute error, and mean absolute percent error. So you can use any of these error functions, and using these error functions, we can classify our model. Okay. So now let's take a look at how K nearest neighbor is used in a practical sense. So here we have our K nearest neighbor code. So first we try to import all our libraries. Then we'll take a look at our data set. Our data set is basically classification of classification of money laundering types. So we are trying to see what type of money laundering is going on here. Okay. So we have the type of transaction. Is the transaction cash in or is it a transfer? So we can probably specify 100, maybe something less. So we have cash in and we also have transfer. So these are the two types of transfer. Is somebody depositing some cash or is somebody depositing via some online method? So we try to find that out. And then what we do is we try to find out how many unique types of fraud we have. We have four, sorry. We have type 1, type 2, type 3, and then we have none. So basically, we have classified our model. So now what does type 1, type 2, and type 3 frauds? Okay. So first party fraud is where the person themselves is involved. Okay. Second is where a family member is involved. And third is where some random person's identity is stolen. So let's say type 1 is direct involvement. That means the person with the illegitimate money is directly using his own name to commit the fraud. Then you have type 2. Type 2 is where they are using some family members. Okay, maybe they had some family members and they are trying to, use their name instead because their name is not on some watch list. And finally, you have type 3, where they are using some random person. This could be an employee. This could be some fake ID they have generated. So you have these three types of fraud. Okay. So what we are trying to here do is we are trying to classify different types of frauds. So we have two possible categorical outputs here. We have is fraud. 1 means yes. 0 means no. And then you have type of fraud. What type of fraud a person is likely to commit. Okay. So type of action we have seen. It can either be cash in or it can be some transfer. Okay. Source ID is where the money is originally sent from. So wherever the money is originally sent from is what we call a source ID. Destination ID is where the money is going. Similarly, amount of money is how much money has been transferred. So here you can notice within the first 10 output, you have the same source ID. You have 10 different destination IDs. None of these destination IDs are matching, but the amount of money is the same. So that means the same person is making these transactions. He is sending the same amount of money from the same source to different locations. And the time is also different. Okay. So he is not doing these transactions at the same time. And this person is involved in type 1 fraud. that means he is using his own name to commit the fraud. Okay, so this is how the data set is structured. Then you try to find out, is fraud unique? 0 and 1. We take a look at the describe. We'll ignore transaction source ID and destination ID. Our focus should mainly be on this, the amount of money. Okay, so we can find out the mean, standard deviation minimum, as well as the maximum. Okay, so the maximum you're looking at is nearly $7 million. All right. So after doing all these steps, then you can see the info. The info is going to tell us if there are any null objects and what are the data types. So we don't have any null objects. So let's see. Let's generate some basic EDA report. So again, we can see the transaction and cash-in transfer is more popular, but cash-in is also quite used. Source ID, we have 1700 different source IDs, 1700 different destination IDs. The maximum amount of money transferred is around 7 million. The minimum is 13,000. Okay. We can also take a look at some basic quantile as well as descriptive statistics. We can see the histogram. We can see how much money is being transferred. E to the power 6 means that we have to add 6 zeros after these transactions, after these numbers. So the highest amount of money, the most frequently transferred money is this value, that is around 0.2. So that is what? 20,000. So 20,000 is the most transferred amount of money based off of the histogram. So then you can see the dates. Is fraud. We can see how many frauds categories are there. So 60% of the transactions are classified as fraud and 40 are not. So that means we have a balanced output in this scenario. Similarly, we have a good balance in this scenario. This is a multi-class classification. This is a binary classification. In both these scenarios, you are doing classification. So we can see the interaction plot. All right. We can see the correlation, not a lot of correlation, no missing values. And then you have the final 10 rows where you have the transfer. So this is the basic EDA that we can perform. Then what we do is we do label encoding. We do label encoding for type of action. Basically, we can encode a type of action using 0 and 1. We can also encode it using one-hot encoding. So now we have converted it all into numerical values. Then we'll use the standard scaler to standardize our amount of money. So here, if I say describe you'll notice the mean is near 0 and the standard deviation is basically 1. And the minimum and maximum is now between minus 0.9 to 2. So we have reduced the scale of our transaction. So now we'll classify it into X and Y variables. We'll add normal money to it. And now we have this type of action as well as the amount of money. So we convert it to an array of values. Then we do a train and test split. So this is the new thing here. So this is where supervised learning diverges from unsupervised learning. So here we had two variables, X and Y. X is our input and Y is our output. X can also be called as independent variable and Y is called as dependent variable. So we split them into test and train. So first we split the X into X train and X test. Then we split Y into Y train and Y test. Okay. And here we specify the test size as 0.25. Let's take it as 0.3. All right. So we do that and we can verify the shape. It is important that these shapes, they match up. Y will have only one. It will only have one value, but X will have the column as well as the total number of entries. So it is important that these shapes, they match up. So now we take a look at the value counts. We take a look at the Y value counts. So here we can see that type of fraud, none type was 941, but here we have 652, 361, 324, and 301. So this is how our data has been split. So then we use our k-neighbors classifier. We built an empty accuracy list. This list will contain the accuracy score at each neighbor. So here we are going to take 5 to 25 neighbors, skipping a step each. So we have 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, and 25 neighbors. Sorry, it will be up until 23 because we have defined the range as 25. So we'll be taking these values of neighbors to try and find out how many nearest values we can take. So we'll define the number of neighbors as I. We'll fit it on X train and Y train. We'll predict the training accuracy as well as the test accuracy. Okay. So let's see what happens when we run this. So red is our training accuracy and this is our test accuracy. So we try to take the number of neighbors where test accuracy is at its peak. So here we can clearly observe a clear peak over here. So this is where we are taking our value. So this would be, I think, 11 neighbors. So at 11 neighbors, we are taking we are classifying it into 11 neighbors each. So you would have 5, 7, 9, and 11. So this is the fourth neighbor value that we were iterating through. So here you can also print the accuracy and we will notice that at neighbor 4, at neighbor 4, our accuracy is the highest. So at this point, we take a accuracy. Okay. Now similarly, we can find out the accuracy for is fraud. Here we are going to take is fraud as an output column. Our X column would remain the same. So let's run it. So now we can see the value of the output values. Okay. So we can test this. So let's let it process. So here what we'll do is, here we'll try to use the confusion matrix. So what we can do is, we can try to define a confusion matrix beforehand. Okay, so let's see what happens when we continue with this. So we again split it into 70-30. So we verify the shape, we build an accuracy. So let's see where we have the highest possible accuracy. So again, here we'll notice that this is not as straightforward as the previous example. Here, how do you find out? How do you take the accuracy? Again, we can probably skip. We can probably use this point where our training test is highest. Here, it is higher than the train, but the difference is not that huge. And again, we are ending up around 11 or 12. So we can take either 11 or we can take 12. Similarly, let's see what happens if we change the number of neighbors here. Let's say we'll go to 30 neighbors. So we'll run this again. So again, it is not going to make much difference. Okay. So here we don't have to use the confusion matrix because we already have the accuracy scores and we can pick where we want to go with. So that is K nearest neighbor. It is the easiest ML model you can implement within supervised learning. All right. So once again, thank you everyone for joining, and we'll meet again on Monday and we'll carry on with supervised machine learning algorithms.